Today on the Perception in Action podcast, a look at the process of perceptual motor calibration. How do we scale our perception of affordances in the environment to our action capabilities? What conditions are needed to allow for effective calibration and recalibration? So it's time for a call to action. Hi everyone, this is Rob Gray from Arizona State University and PerceptionAction.com. Welcome to the Perception in Action podcast, where I discuss how psychological research can be applied to improving performance, accelerating skill acquisition, and designing technologies. In today's episode, a look at the process of perceptual motor calibration. Back in episode 53, I discussed the three components in direct learning theory. Imagine that you are a defender in a sport like soccer, basketball, hockey, or football, and you want to intercept a pass. This is the first component, education of intention. You have focused on the goal you intend to perform, interception. Next, which perceptual information should you use to intercept the ball? Is it the perceived distance from you? No, because that doesn't take into account the speed of the pass. The ball's speed? No, that doesn't take into account the distance the ball has to travel. To successfully intercept a pass, we need to pick up the time to passage information, how long it will be before the ball passes by our body, which takes into account both speed and distance and is specified by a variant of the information source tau. Learning to use this information is the second component in direct learning, education of attention, learning to pick up information that is specifying for your goal task. So, now we have a goal or intention, we have attuned to the information that is specifying for it, but there is still one more component. Imagine that using tau information, you perceive that the pass your opponent just threw will go by you in 1.5 seconds. Should you try and move to intercept it? It depends. Can you get to the ball in time? If you can't, then trying to intercept the ball will likely create a scoring opportunity for the opposing team and earn you a spot on the bench. What we're talking about here is the perception of an affordance. Let's call it interceptability. When we pick up the time to passage information from a pass, we need to determine whether or not the pass affords interceptability or not. To do this, we need the last component of direct learning, calibration. Specifically, we need to scale the perceptual information by our action capability. Whether or not a pass with a time to passage of 1.5 seconds affords interceptability depends on how quickly we can cover the distance, an action capability that will vary from performer to performer. In other situations, it will be our body dimensions, for example the length of our arm or leg, that will be the scaling factor. Another way to think of all of this is, perceptual motor calibration is necessary for distinguishing possible from impossible opportunities for action in our environment. In today's episode, I want to look at this calibration process in a bit more detail. How is it achieved? Is it functional? So that, for example, the calibration you develop for intercepting a soccer pass with your left foot transfers to interception with your right foot? Or is it anatomical, so that we develop specific calibrations for different body parts? Or is it both? What conditions are needed in practice to allow an athlete to effectively learn to calibrate and to recalibrate when their action capabilities change? For example, due to aging, injury, equipment change in the goal, or some other factor. So let's dive in. Before looking at the process of how calibration occurs, a first question we might ask is, how effectively are perception of affordances scaled to our action capabilities? The first work addressing this issue was by Bill Warren. In a 1984 study, he asked people to indicate the maximal and optimal height of stairs that afforded climbing. He used participants of varying heights and presented them with a variety of different step sizes. What was found? Independent of their height, participants almost uniformly perceived steps that were 1/4 of their leg length to be optimal for climbing, and steps that were roughly 90% of their leg length to be maximal. So in other words, they were clearly scaling the perception of possibilities for action, the affordance of climbability, by their own individual action capabilities, determined by their body size in this case. The 90% value represents an important value in the perception of affordances. It can be thought of as an action boundary. For heights below this value, climbability will be perceived. For ones above it, it will not. and the performer will have to perform some other action if their intent is to get up the stairs. Since this seminal study, this basic scaling effect has been demonstrated for a wide range of actions, including things like passing through an opening or gap like a doorway. An interesting twist on this behavior was examined in a recent study by Franchak and Adolf, where it was shown that the perception of the affordance of passability of gaps made by pregnant women almost perfectly tracks their changes in their body dimensions during the course of pregnancy. So this is an important point. Calibration for many of the actions we perform is a dynamic, ongoing process. It's not simply just learning a constant like your foot length. It often involves updating the calibration based on changes in action capabilities. This process of recalibration in response to changes in our action capabilities has been studied in many different ways. The classic example being prism adaptation, where you have a performer recalibrate the act of throwing or walking in response to a distortion of the visual information by the prism. For those that want to see this in action, please check out vlog number 5 on my YouTube channel. In 2017, Van Andel and colleagues conducted a systematic review of studies which have looked at the process of recalibration to changes in action capabilities. The general findings across a wide range of studies were the following. The time frame required for calibration is highly variable, with some studies showing it happening in 1 second of exposure to altered conditions, while others showing it takes up to 30 minutes. Regular listeners of the podcast can probably guess what the factor is responsible for this big difference. Yes, it is the degree to which participants were allowed to explore the new perceptual and action space, and/or the amount of feedback they received about their movements. As an example of this, I can tell you about the weighted baseball bat study I did in 2007, and I've talked about a few times already on the podcast. We found that when you gave a batter a heavier or lighter bat, it took roughly 5 to 10 swings for any noticeable changes in their hitting performance to disappear. However, if we allowed the batter to wield the bat in their hands, that is just moving it around, not swinging, before hitting, the number of swings required to recalibrate was cut in half. So clearly, calibration requires exploration of the environment so that self-organization can occur. We also found in our study that the way in which batters recalibrated fit nicely to their action capabilities. That is, batters that could handle a heavier bat without losing swing velocity just swung harder, while those that couldn't just adjusted the timing of their swing. The main point here is another important one. Calibration requires information that can only be perceived through exploration. Okay, so we've seen that our perception of affordances seem to be effectively calibrated for our action capabilities. And, given the ability to explore, we can relatively quickly recalibrate when either the perceptual information or our action capabilities are changed. Now let's look a little more at how this process of calibration actually occurs. To address this question, we first need to look at an issue that I've touched on many times in the podcast, the units of perception and action. As I've tried to stress several times now, we do not have rangefinders, radar guns, tape measures, GPS, etc. in our head. That is, we do not perceive the world in the units of physics, meters, feet, miles per hour, etc. Optical information is angular, not linear. The classic example of this is one I talked about way back in episode 5. If a large object were approaching Earth and we could only use our eyes, we would have no way of knowing whether it was a very large object that was far away or a smaller object that was closer to us, because all we would have would be the angle projected by the object on our retina, which would be the same in both cases. We can't directly derive linear extents, how wide the object is in feet, from angular visual information we have access to in this situation. So, how then can we know, for example, how many feet away an object is in order to reach out and grasp it? Fortunately, in normal, everyday examples of interacting with objects, we do have a way of scaling the angular information we receive on our retina in terms of linear extents. For example, imagine you're standing looking at an object on the ground, say a soccer ball lying on the field. This essentially forms a triangle. On one side of the triangle, you have the field between you and the ball. In other words, the distance of the ball from you. On another side, you have the distance between your eye and the ground, what we commonly call your eye height. And finally, the hypotenuse of the triangle is the projection of light from the ball to your eye along your line of sight. The visual information in this situation is what is called the elevation angle. the angle formed at your eye by your line of sight and the ground. Without going into all the math, using this elevation angle, which is available visually, and your eye height, which you can learn through experience, you can derive the other side of the triangle, the distance of the ball from you in linear units. In this case, the units will be eye heights. If all that made absolutely no sense to you, then the main takeaway message is that we can scale angular visual information using particular body extents, like eye heights, that are part of the viewing geometry. Another example of an extent that can be used is the distance between your eyes, called the interpupillary distance or IPD, which can be used to scale vergence angle when we look at an object. Turning from perception to action, if you think about it, there's a scaling problem there too. Knowing how far away an object is that we want to run to in meters or feet is not really helpful. We need to scale it so that it is in units of action. In this case, we might want the distance expressed in the number of stride lengths so that we can effectively control the action. Bringing this all back to the issue of calibration, in 1998, Jeff Bingham and Chris Pagano introduced the mapping theory of calibration, in which it is proposed that calibration is a mapping from embodied units of perception, like eye heights and IPD, to embodied units of action, like stride lengths. So through exploration of my environment, I essentially learned something like how many stride lengths it will take me to cover a certain number of eye heights of distance. It is this information that allows for scaling of visual information in the perception of affordances. Again, it's important to emphasize here that this process will be dynamic, because these sizes will change over time, with different timescales of change for different body parts. The IPD unit changes in size slowly over the course of our development and then remains stable, unchanging during adulthood. The same is largely true of our arm length units of reaching or stride length units of walking. In contrast, the eye height unit changes frequently throughout one's life, with change in posture or change in surfaces we are resting on. For example, when a person changes from seated to standing posture, the eye height unit changes. When a person selects footwear for the day, choosing between low-heeled and high-heeled shoes, that will also perturb their standing eye height unit for the day. This mapping among embodied units theory of calibration makes some important predictions. First, calibration of a given action performed with one limb should generalize or transfer to another limb performing the same action, because the units, eye heights and arm lengths, involved are the same. So calibration is functional in that it is specific to the type of action. Second, limb-specific calibration enables adaptation to anatomically specific changes in a limb, for example due to injury, weighting of a limb, fatigue, etc. Units of action are embodied, meaning that the anatomy of the limbs contributes to the scaling of such units. For instance, if one arm is longer than the other, or the range of joint motion is restricted in one arm, this affects the size of the unit of action for reaching. For example, what is at maximum reach for one arm might not be the same for the other. The nature of the unit is the same for both arms, but the size is different, meaning the calibration will be slightly different. Thus, the arms must be calibrated relative to one another. Therefore, calibration must also be anatomical. In a 2014 paper, Bingham and colleagues tested these predictions using a reaching task in which haptic feedback was used to distort the perceived distance. In experiment 1, participants calibrated their reaching movements in the presence of this distortion by practicing with their right arm and then were tested with their left arm. As predicted by mapping theory, there was almost perfect transfer between arms because the units required for calibration were the same. Calibration is functional in that it transfers between tasks that use the same units of perception and action. In experiment 2, participants practiced in conditions in which the distortion applied was different for the left and right arms, simulating what might happen, for example, if you had very different ranges of motion for the two. After practicing, the arms were switched. This produced very poor transfer and large reaching errors. In other words, as predicted by mapping theory, under these conditions, participants learned an anatomically specific calibration for each arm, not one that applied generally to both. So in other words, calibration is both functional, in that it can transfer between similar tasks, and anatomical, in that it is specific to any unique characteristics of a particular body part. Okay, to sum up, in today's episode we looked at the process of calibration, emphasizing the point that even when you have detected perceptual information that is specifying for your goal, that is, your attention has been educated to the appropriate information, you still need to place this information on an action-relevant scale. Calibration is this process of scaling a perceived information variable to the relevant action for your goal. In terms of take-home messages for coaches, examining the process of calibration again emphasizes the need for opportunities to explore the perception action space in practice. Calibration requires information that can only be gained through exploration. This will be particularly important when any changes occur that distort the mapping between perceptual units and bodily units, for example due to injury or equipment change. Okay, that's it for today's episode. Remember, you can contact me at robgray@asu.edu or follow me on Twitter at ShakyWeights. To find out more about the podcast, please check out perceptionaction.com. Finally, to support the podcast and receive bonus materials, including an extra monthly episode and transcripts, which now include transcripts of interviews too, please head over to patreon.com/perceptionaction. This is Rob Gray from ASU. Cheers for now, and keep 'em coupled.